Hello again. This is video 2 for section 2.1 on functions. I'm going to spend this video talking about finding domains from equations. There are three types of equations that we need to be careful when we're looking for domain of a function. And the first one is when our function is defined by a rational equation. So FCN is the abbreviation for function. Yeah. In a rational function, we have a polynomial in the denominator, and since there's a denominator, we know that with an unknown, we know that the denominator cannot be equal to 0, or there would be no function value defined at, because there is no function value defined where the denominator is equal to 0. Let's look at an example. If we look at it, f of x equals 1 over x minus 8. X minus 8 cannot equal 0. So if we take a look at this non-equation and solve it for x, that means that x cannot equal 8, because that's what would make this denominator 0. So that means then that the domain of this rational function will be negative infinity to 8 union 8 to infinity. Notice I did not include 8. Or another way to say it would be to say all x such that x does not equal 8. Okay. The second type of function you have to be careful about when you're looking at its domain is a function that has an even root or radical. Let's call it an even root function. There can be no negative value under the even root, because we can't take an even root of a negative number. So let's take a look at an example of this. If we think of f of x equals the square root of x plus 1, what we call the radicand, which is the number underneath the radical, can never be negative. It can equal 0 because the square root of 0 is 0. But if we take the square root of a negative number, we'll get a complex number. And when we're talking about graphs and functions right now, we're talking about real numbers. So, since x plus 1 cannot be negative, we set up an inequality that says x plus 1 must be greater than or equal to 0. Then we solve for x, and this tells us that x must be greater than or equal to negative 1. This sentence translates to being that the domain is everything including negative 1 up through infinity. If we saw it on a number line, we could see that we would shade in, put a bracket here at negative 1 to be included, and shade everything all the way up to infinity. Or, of course, we can put it in set builder notation that says all x such that x is greater than or equal to negative 1. The third and final type of function that we need to be careful about when we're looking at domain, in this course specifically, are rational functions that have even radicals in their denominators. So it's kind of a combination of the first two functions that I talked about. So it's a rational function, oops, that is an M, not an N, function with even roots in its denominator. What happens here is that the radicand must be greater than 0, and, so let's say the radicand must be greater than 0, and at the same time, no value of x can cause the denominator to be 0. I need to go back. The radicand must be greater than or equal to 0. And at the same time, no value of x can cause the denominator to be 0. Let's take a look at this example. If we take the function f of x is equal to 1 over negative 2 plus the fourth root of negative 3 minus x plus the fourth root. Sorry, technology's a little challenging here. There we go. This extends all the way out. We can look at these two conditions. First of all, the radicand must be greater than or equal to 0. So we say negative 3 minus x greater than or equal to 0. If I add x to both sides of this inequality, I get that x must be less than or equal. Turning it around, it's easier to read, as x is less than or equal to negative 3. But at the same time, and we must have that the denominator, which is negative 2, plus the fourth root of negative 3 minus x, cannot equal 0. If I add 2 to both sides, this is the same thing then as saying that the fourth root of negative 3 minus x cannot equal 2. So we need to not include the values of x that are going to make this even root equal to 2 in the denominator, because if we were to include them, that would make our denominator be equal to 0. So how do I solve this? Well, I can raise both sides of the equation to the fourth power. The fourth root and the fourth power cancel, and we end up with negative 3 minus x cannot be equal to 16. Now I'm going to add x to both sides and subtract 16 to both sides. And this is telling me that x cannot be a negative 19. Look really quickly just to see what would happen if x equaled negative 19, right? The denominator then would be negative 2 plus the fourth root of negative 3 minus negative 19. That's negative 3 plus 19, which is 16. We would get negative 2 plus the fourth root of 2, which equals 0. And that is not allowed. Okay, so now we have two conditions on the domain of our function f of x. Let's put them together in a domain statement. So we could say that the domain of f here, has to be less than or equal to negative 3, but it can't equal negative 19. So if we start at negative infinity, we go up to negative 19, we cannot include negative 19. So everything up to negative 19 and everything past negative 19, but not including negative 19. But then we stop at negative 3 and include it because it's less than or equal to. So take a quick look at the number line here. If I put 0, negative 3, negative 19, I know that there has to be a hole at negative 19, and my domain is everything less than 3. The graph of the domain would look like this.